Problem number 2, part A, supposed to state the form of the limit. That means a determinate or indeterminate form. Evaluate the limit. If it doesn't exist, right, doesn't exist. A says you may use L'Hopital's rule. So let's first see if this limit is indeterminate. Indeterminate means that both the top and the bottom are equal to 0, or both the top and the bottom are equal to infinity or negative infinity, or some combination of that. L'Hopital's rule can be used if it's an indeterminate form. So I'm just going to rewrite this from the beginning as a fraction, because L'Hopital's rule can only be used if it's a fraction. I'm going to move this to the bottom of the fraction by changing the sign of the exponent. Now if I evaluate this limit, the top, if you put negative infinity into the top, you're going to get negative infinity minus 6, which means it goes to negative infinity. And the bottom, if you put negative infinity in for x, you're going to have e to the negative infinity is like e to the infinity, so that goes to infinity. So the form of this is indeterminate. Indeterminate. I'm not sure if that's how you spell it because I'm a terrible speller. If it's indeterminate, you can use L'Hopital's rule. L'Hopital's rule is pretty awesome. It says that we can take the derivative of both the numerator and denominator and then see if we can evaluate the limit. The derivative of x minus 6 is 1. The derivative of e to the negative x, you take the derivative of the exponent, derivative of negative x is negative 1, times e to the original function. Now I could rewrite this as the limit as x approaches negative infinity of negative e to the x. I just made the exponent positive and moved the base e to the top of the fraction. Now to evaluate this limit, we're going to put a negative in for x, negative infinity, which means this is negative 1 over e to the infinity, which means this is negative 1 over infinity. If the bottom is growing without bound, going to infinity, and the top is a constant, that means that this limit is approaching 0. Hopefully that made sense, kind of sloppy. B, evaluate the integral. Hint, use symmetry. Well, this upper and lower bound have a symmetry because going from negative 1 to 1 is symmetric with the y-axis. So there's some rules here. If a function is odd, let me remind you what an odd function is. If it's odd, it's symmetric. That doesn't look very good. It's symmetric to the origin. So that means like if you took this and reflected it here, then reflected it here, it would be the same image that you saw. An example would be y equals x cubed is odd. This is an odd function. So what does that have to do with if it's odd? If you find the area under the curve between it and the x-axis in the curve, it's a positive area up here. Here, it's going to be a negative area. Those areas will be identical if it's an odd function, which means that if you add those together, it's going to equal 0 because you're adding the same number to itself. One's positive, one's negative. Sine is also odd. Sine normally looks something like this. Since this is negative, it's reflected over the y-axis, so it would look like this. But regardless, it's odd, so that means these areas are going to cancel out because it's the upper and lower bounds are symmetric with the y-axis. So those first two parts is equivalent to saying that the areas are 0. Pi is an even function because that's just a horizontal line. So what that means, we can just find the area from 0 to 1 and then double it because it's going to be the same from -1 to 0. I don't know why we would want to do that, but it says use symmetry, so we're going to. This little fella is also an even function, and I'm not sure if you have to show why you know it's even, and if you don't know why it's even, let me know and I'll try to answer you. So let's try to integrate this. So once again, if I just break this apart from -1 to 1 of 2x to the 17th dx minus integrating from -1 to 1 sine of x dx, both of those are going to be 0. If I add to that integrating pi from 0 to 1 and then I double it, that's the same as integrating from -1 to 1. You could do either one, but the clue up there says to use symmetry. Then I add to that, since this last term is also even, I could integrate from 0 to 1, then double it, or I could integrate from -1 to 1. 1 over 1 plus x squared dx. Once again, that's this, plus 2. Integrating pi is going to be pi x, that's the antiderivative evaluated from 0 to 1, plus 2. I don't know if you recognize this or not, but that is tangent inverse of x, evaluated from 0 to 1. That's something you need to memorize. Integrating 1 over 1 plus x squared is tangent inverse of x. I actually forgot that and looked that up when I solved this problem. So finishing those two zeros that we have here, those are just going to be 0, obviously. So then we're going to have 2 pi times 1 minus 2 pi times 0. Brackets are just from Thassus, doesn't really change our answer. Plus 2 times tangent inverse of 1 minus 2 times tangent inverse of 0. So here we're going to get 2 pi minus 0. Over here we're going to get 2 times tangent inverse of 1. Tangent inverse of 1 equals some angle is the same question as saying tangent of what angle is 1. Those are equivalent statements. You don't need to write that down for your work, but I just want to make sure you remember that from pre-calc. Tangent's equal to 1 when your y and x values are the same. That happens at 45 degrees, or pi over 4, minus 2 times tangent inverse of 0. Well, when does tangent equal 0? That's when you have y over x, when y is 0. Y is 0 at 0. So this ends up being, assuming that I didn't make any mistakes, 2 pi plus pi over 2, which would end up being, see, 2 pi is the same as 4 pi over 2, so this will be 5 pi over 2, or 2.5 pi. They do not like to give you lots of room here, do they? So that concludes part B. Part C, this is the second fundamental theorem of calculus, or maybe it's the second part of the fundamental theorem of calculus. I forget what it's called. I think it's the second fundamental theorem. And that is, if you're taking the derivative of an integral, those things kind of counteract each other. This is going to be equal to, you take the integrand and you replace the variable in it with the upper limit of integration. Color code it for your viewing pleasure. Then you multiply it by the derivative of the upper bound. It's the chain rule, essentially. That's what just happened. Natural log of x integrates, its derivative is 1 over x. So that means this ends up being four minus sine of natural log of x divided by x when you put that together. Pretty confident about that. D, this problem seems oddly out of place. So hopefully I'm doing this right. I mean, 99% this is right, but we don't ever do this in calculus. So all this is saying, first of all, this is summation. Integrating is also summation. See how it looks like an S? Greek letter sigma starts with an S. It means to sum. All you're going to do is you're going to take this 1 and put it in for the case, and then add to that, putting in the next integer after 1, which is a 2 in for the case. Then you're going to put in a 3 in for the case. So it looks a little something like this. You get 6 times 1 minus 1 over 1 plus 1 plus. Let me also color code this for your viewing pleasure. Then we're going to have 6 times 2 minus 1 over 2 plus 1. Keep changing k by increasing it by 1 integer until you get to the upper bound. And the upper bound is this 3 that you see here. So this simplifies to 6 times 0 divided by 2 plus 6 times 1 over 3 plus 6 times 2 over 4. It's going to be 0 plus 2 plus 3. This sums to 5.